Hello everyone and welcome to our 94th webinar series today. I'm very pleased that this new innovative virtual forum has been so well received. It has given us an opportunity to scale the event to a wider community and be even more inclusive. It's a notable achievement to mark 25 months of cooperation between all AABN members to leverage AABN as critical driver of development. Since the launch on 27th June 2020, the forum has garnered a lot of interest and excitement from all regions of the world, with a cumulative attendance of over 8,000 attendees from around the globe participating in more than 93 virtual sessions, which were organized by AABN team with over 100 plus speakers. The forum has had the best balance of participation, both in terms of members, regions, and gender. From the beginning, our goal has remained the same: to help entrepreneur community replicate examples of good and sustainable use of AABN, and to encourage everyone to make good and timely use of the rich database available. Artificial intelligence started off with great promise in the early 80s. Artificial intelligence empowers professionals from large global manufacturing and oil and gas enterprise with data-driven insights to improve production process and optimize assets. AI enables intelligent industrial operations by optimizing production process, predicting maintenance, driving energy efficiency and savings, and more. Don't have a data science background? No problem. Join our expert, Mr. Sudhanshu Kashyap, Principal Data Scientist, Symphony AI, on this webinar, as he provides a clear roadmap for chemical engineers to get started with artificial intelligence and machine learning. Sudhanshu will cover critical steps in defining an AI ML project and share lessons learned from process and industrial engineers to help you identify key opportunities to apply AI successfully. In the past decade, the machine learning field has grown exponentially. It has succeeded in solving problems we were trying to solve for decades. In this webinar, Mr. Sudhanshu will talk about what machine learning is and how it manages to solve difficult problems. We will have an overview of various problems and the techniques used to solve them. The really interesting and intellectually challenging problems lies in developing conceptual frameworks as hybrid models, mechanism-based causal explanations, domain-specific knowledge, discovery engines, and analytical theories of emergence. These breakthroughs would require going beyond purely data-centric machine learning, despite all its current excitement, and leveraging other knowledge representation and reasoning methods from the earlier phase of AI. They would require a proper integration of symbolic reasoning and data-driven processing. Mr. Sudhanshu will discuss opportunities going forward. I have the pleasant duty of welcoming and introducing our distinguished guest speaker, Mr. Sudhanshu Kashyap, at Beyond Theory, Artificial Intelligence, Machine Learning, and Applications in Chemical Engineering. He will give an insight on the role played by artificial intelligence and machine learning in chemical engineering applications. Sudhanshu is a principal data scientist at Symphony AI. He is responsible for development and implementation of domain-informed AI-based solutions for chemical, oil and gas, process, mining, and metal industries. Prior to joining Symphony AI, Sudhanshu has worked in GE as lead technologist for a decade, developing physics and database solutions for power, water, and oil and gas industries. Mr. Sudhanshu has a BTech Chemical Engineering degree from IIT BHU Varanasi campus and MS in Chemical Engineering from North Carolina State University, Raleigh, USA. Today's webinar will enable the attendees to strengthen their knowledge about the role of AI and ML in chemical engineering. During today's discussion, our guest speaker will introduce the computational means and methodologies available to enable computers to perform intelligent engineering tasks. The attendees will be gifted with information and knowledge about industry needs, latest technical appraisals, and research areas related to this field. I wish you all interesting and productive webinar and look forward to a collaboration in the weeks and months to come. Thank you. Over to Mr. Sudhanshu.
Thank you, Gopi sir. Good morning, everyone. It's my pleasure to present to this prestigious forum. I'm going to share my screen and start the presentation. Is my screen up now?
Okay.
Okay. So we all are hearing this buzzword artificial intelligence lately. So we'll try to understand in this presentation why now, and we'll also try to understand what is artificial intelligence and machine learning. What is difference between these two terminology we keep hearing very often, and we look into some machine learning methods at very high level kind of overview. And then we'll jump into some application part, and we see how AI based model or methods can be applied to ammonia manufacturing process. And then we'll also cover a second use case in direct reduced iron process optimization using artificial intelligence. So let's get started on these topics. So why artificial intelligence? And the major reason is a key technologies which is needed for artificial intelligence had exponential growth in last couple of decades. So the first one is a computing, and here what you see a graph of processors being in operation from 1970 to 2018, and we see that is started from 1,000 processors to now we have hundreds of billions of processors working. So that's the scale of computing we have available now, and we all witnessed the transformation in telecommunications. So we could see in both terms, data storage and data transfer. So internet speed has been enormously improved in last few years all around the world, and that is another key driver. And third one is the sensors. So now we have availability of cheap sensors, and we have a connected devices. So everywhere we are generating lots of data. So 97% of world data is being generated in last few years. So that's the stat we are looking at. So now we have all these key critical components falling in place, and that is driving the growth of AI technology. So what companies are doing? So you utilize the data technology as a competitive advantage, and then how we do it. So you need to do certain steps. The first one is collecting the data. We have IoT devices. Now we have wireless sensors, chip sensors. So we could install these sensors and collect the data. And once we collect it, we need to store those data and store. For storage, now we have a plethora of technologies available. So there are cloud platform, distributed database, blockchains, and you could do it in your local data store as well. And then also the data transmission part. So we need to transfer data from one place to another place, and we that's where our telecommunication technologies like Wi-Fi, Bluetooth, 4G, 5G comes into the picture. And finally, the process that data to bring the insights and useful information out of it. And that's where all this artificial intelligence, with machine learning, natural language processing, neural network, deep learning, all these kind of technology falls in this category. So now industries are trying to use all these technologies, and what is the objective? And it's the objective is reducing operational costs. So how we do it is like predict failures or mitigate failures, optimize overall plant performance, improve the efficiency. So these are objectives, and you know these objectives are always there since the industrial revolution, and continuously we are trying to improve the plant profitability by doing all of this. So what is problem there with our conventional approach, where we deploy physics-based models? So we do physics-based analysis and then and do all of it. So let's look into what is challenges present in those areas, and the challenges are high complexity. So if you look at industrial problem, chemical engineering problem like combustion, heat transfer, mass transfer, or chemical kinetics, they're very complex. And if you try to model it with very high fidelity, and we go and start increasing number of model parameters, and then complexity of model increases exponentially. So why this happens? Because first is dynamics, and we see we change certain inputs, and then our process reacts to it. So we need to model that dynamics, and all the time we have changes into our process, whether disturbances to the process. So we need to model that. And then non-linearity. So we see most of these mass transfer, heat transfer, or all these problems what we work on in chemical engineering, they are highly non-linear. So that needs to be modeled such that we could predict it. We could simulate those situations. And of course the variability, and variability is always there in both time and space. So that variability also needs to be modeled together. So if you want to put a mathematical model of a process or system, industrial system, then where we want to do dynamics, non-linearity, and variability together, then we go our partial differential equations and try to model it, mimic the behavior using the mathematics and physics. And we all have seen and have used into our past these kind of problems, and we see how hard it is to scale this and do it quickly. So basically it becomes a kind of non-tractable solution if you want to do it on a scale and try to model each and every system with the details. So we go and then try to solve it by doing a deconstruction. So divide and conquer, right? And that's where comes is a finite element modeling, multi-body dynamics. So we take the problem and make it a smaller problems and try to do it. And sometimes we do like localize it, simplify it. So we convert these partial differential equations to ordinary differential equations to have a much simpler lumped model and solution. But still it's quite complex. Means if you want to do it at scale, it's need a lot of amount of time and compute to get it working in real case scenario. So now comes the data-based AI models. And what database AI models does is it discretize it. So basically all these differential equations, what we were talking earlier, we could make it as a discrete data point. And if we have enough data, then we could give AI models to learn about the process, or we could build a process model, or also we call it digital twin of the process or system using the models. And here the all hard work is being done by these algorithms and the compute power what we are utilizing. So this makes this whole problem easy to manage and also easy to scale. But the requirement here is a data, and we should have enough data where these AI models could learn the process behavior variations, all these dynamics what we are talking about from that given data. So now if you look at what is different with AI solutions compared to the conventional solutions, so it has good enough fidelity. So if we have we provide it to enough data, then the details will be very accurate, and we could do a very detailed assessment of the solution or problem. And another problem is adaptive. So these models and algorithms, they can learn continuously from incoming data. It's not a static model. So once we put these models into operation by training it on historical data, and now since process always evolves, conditions changes, so we could keep feeding that information back to these models such that they could tune themselves and tweak themselves to be relevant. So that adaptive part is inbuilt in these AI solutions. And computationally fast, so it's relative. Now we have a lot of compute available, and we have GPUs, and now coming TPUs. So these are facilitating even very complex calculations to be done very quickly in real time, and we could get inferences and insights very quickly. So these are some changes what happened in recent times, which made AI solutions feasible, and that's why we are seeing a lot of buzz around it and lots of applications. But still, this whole AI implementation in industrial is in its infancy stage, and it will evolve over next 5 to 10 years of time. Okay, so next let's move to this terminology, what we keep hearing, the artificial intelligence and machine learning, and let's learn what is the difference. So when we talk about artificial intelligence, it's say that a machine or system that seems or act like humans. So that's the you see human intelligence, and if a machine is mimicking similar intelligence, we call it artificial intelligence. You might find a lot of different definitions. So that's fine. That's okay. But this is what I think most appropriate for artificial intelligence. And now when we come and talk about machine learning, so as a definition goes, a machine that takes in data and learns things about the world. So basically a machine which learns from the data. So and in all this terminology, basically machine learning are algorithms, computer algorithms, which takes data and learns about it. So if you look at these two terms, so machine learning is a way to achieve the artificial intelligence. So once a machine learns from data and understand how data works, how system works, now they can take a decision more like a human, right? So machine learning is a way to achieve artificial intelligence. That's how we should see it and differentiate it. So if you look at uh, AI is a kind of a very generic terminology, and machine learning, ML, is a part of it. So basically, it's facilitating AI. And again, means you could have a machine learning which is not learning about world and all, or do something else. So you have something out here also. But there is a many other way of achieving the artificial intelligence. And if you look at the very early AI systems, the rule engines were came in place, and they are also artificial intelligence. You see machine vision, machine speech, robotics. So it's kind of overlap of multiple technologies together, which defines the artificial intelligence. And you might see that these are being used very interchangeably everywhere, and there is no perfect separation. So if you look at the industrial problems, most of them fall into this machine learning category, where we try to learn the process behavior or asset behavior using the data and algorithms. So you might see artificial intelligence and machine learning being used interchangeably in the industrial or even other domains as well. So don't get confused between these two when you comes to terminologies, these terminologies. Just that's why I wanted to highlight it. So now get into next stage of presentation and look into some popular machine learning methods, and we'll keep it very high level because of time constraint we have here. So when we, you also might have heard that supervised and unsupervised learning. And supervised learning is where we feed labeled data to the learning algorithms. So for example, see here we have some images of the cat, and we are labeling them. We're telling that this is also cat, this is a white cat, but this is also cat. And then this is not a cat. And objective for AI model is to learn and classify whether given image is a cat or not a cat. And an AI model learns it, and then it produces a predictive model. And now once we have predictive model, we supply this one image. This is again the cat image, but a bit different than what it has learned from. And it says that, okay, it goes to predictive model, and it tells that, yes, it's a cat. That's the result we are getting out of it. So these kind of learning process, where we give a level data, we tell upfront the learning algorithm what is input coming into the models is called supervised learning. And there is a two part of it. The first part where we are supplying this data for learning purpose is called training the models. And then the second part where we are inferring, we are giving a new image and then asking it to recognize whether it is cat or it is cat or not a cat. It's also called a scoring, testing, or inference making. So these are the synonymous names what you'll hear. So that's the supervised learning, and these are some few methods I have just put it here, very popular ones. But there are plethora of AI models and methods available for doing these kind of supervised learning. So next one comes is unsupervised learning, and unsupervised learning, you see that here we're not saying this is cat, this is dog, this is bird. We are not providing that information and giving all these images to a learning algorithms and then ask it to separate them in a logical groups. And what it does, it's say that this is one logical group. So basically it has taken all cats and put into one category, taken bird and put into one category, and then taken dog and put into another category. So the learning algorithms looks into all these objects and try to see that which have similar features, which has similar attributes, and based on that it's classify them in a group. So these kind of learnings where we are not supplying the information about what is what, we are not labeling them, is called the unsupervised learning. So this is the difference between supervised and unsupervised learning, and most of the algorithms are fall into these two categories. We also see semi-supervised methods, and when we'll come to use case, I'll explain that. For now, we'll skip it. So again, there are many methods available. Few popular ones which you can start with is I've listed here. So now, once we have learned about supervised, unsupervised learning, and then what are the different kind of learning algorithms, common types of applications available, and it starts with a regression, and it's very simple. You would have done many times in Excel, like fitting a curve to a data, and basically that is regression. And here in industrial domain, we could apply it to do soft sensing using some advanced machine learning algorithms. So for example, say we want to predict heat exchanger fouling conditions. So we supply all temperature flow conditions of the heat exchanger, train the models of fouling behavior, and then just with those inputs, it could predict the fouling condition of the exchanger. So that's a kind of a regression model. A classification is where we classify with limited categories. So for example, we detect a fault in equipment, and we want to understand whether it is bearing problem or coupling problem. So that becomes a classification problem. So based on the features or results we are getting out of these algorithms, we could say that yes, it is a bearing problem, or it is a coupling problem, or we could do also multi-class. So we have more fault modes, then we could bring that in and also identify what it is. Again, forecasting. So forecasting is taking any parameters and extending into future and see that how it will evolve in coming time. We very often we see this weather forecast about rain coming in, or how temperature is going to be. We keep seeing it. Very similar, we could do like a production demand forecast, or if we are running a process, then we can do a quality forecast based on how the process parameters are. So that becomes very useful when we get into a process optimization kind of problems. And again, anomaly detection. So anomaly detection is it's more about detecting fault into assets or process. So for example, something is unusual, what we are seeing in a process or running asset. If you can identify it upfront, then that comes into anomaly detection. It is also used very often into fraud detection. So you might see a fraud credit card transaction, and the bank get alerted that something going wrong. Then they can call and verify those kind of these kind of algorithms being deployed there. And computer vision, where we do a machine learning in industrial domain to do like defect identifications. For example, say we are producing some product, say uh, 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 steel rods or something like that, and we are seeing scratches on it, right? So a computer vision could look into it and tell that, look, we are producing a faulty product here, or maybe very sophisticated hardware component like hard drives. So we look the images of the produced hard drive, very high resolution images, and then ML methods could tell that whether there is any defect on that particular hard drive or it is good. So those kind of those are some application of computer vision in industrial domain. And of course, means all of us this have seen this face detection. Your phone does it, so it groups similar people into different folders if you want, and you must have seen the this on Facebook and similar social networking sites. And the other part comes natural language processing, also known as NLP. And here, the application in industrial domain could be extract insights or trends from lab reports. So lab reports are mostly textual. So automatically you consume it, analyze those texts, and then or maybe multiple lab reports together and get insights out of it. Look into maintenance logs, what operators has been written, and then take a consolidated insights about the whole process or asset system. Other applications, you might see the translation. So you have see how Google Translate works. One language to another language, it utilizes language, natural language processing. And also very often you now have been interacting with chatbots whenever you go and then put some questions, and then a chatbots replies to it. So that is AI system, natural NLP system working in the back end. And we all have seen this recommendation engine. So you go into these OTT sites, Netflix and all, and then they do a recommendation that, okay, look, this is something you might be interested to watch, and you watch something based on that. It will make some more recommendation based on your taste and what kind of the content you watch. And also e-commerce site keep recommending you that you might be interested in these items based on what purchases you are doing, what kind of search you are making on those e-commerce sites. And industrial domain, we could utilize these kind of engines to do some action recommendations. So say you detect some fault and you want to recommend some action, then a similar system could be deployed to do it. So that's a very high level. I try to cover most popular machine learning algorithms and then their application, particularly industrial, and some examples are non-industrial domain as well. So so now, if you want to implement these kind of models and methods, what kind of toolings are needed, and the infrastructure we have is one is a Python-based infrastructure, which is most evolved using doing ML kind of methods, and these are some very common popular machine learning libraries available in Python. So you see PyTorch, TensorFlow. They can be used for these neural network kind of models, and a lot of basic machine learning models can be available in scikit-learn. And all these libraries like NumPy and all, they do data manipulation, array manipulation, which is very essential part of doing machine learning. And if you want to do scientific computation, optimization, those kind of problems could be solved using SciPy. And this matplotlib is a library to do visualization, because once we do this machine learning, we want to look at results, visualize them, and understand how it is looking. So visualization is integral part of the machine learning, and matplotlib a very good start if you want to get into these fields. Okay, so now we have covered some basics about machine learning, and then we'll get into some application part. And the first one is I'll talking about is a CO2 excursion anomaly prediction in ammonia manufacturing plant. And before I jump to the real use case, what is being done in this particular, I'll give some background about anomaly detection. We briefly talked about it in previous slides, but we'll go a little bit in detail such that you could follow the use case better. So what is anomaly detection? And if you look at definition of anomaly detection, it is identification of events or observation which are different from majority of data. So see, if you given this kind of a line chart and somebody asks you to identify what is anomaly here, very clearly you could point it out that these spikes, what you are seeing is anomalous because they are very different than remaining or majority of data what we have on this particular parameter. But this is something coming out of ammonia plant, CO2 removal unit output of that, and it is result of interaction of hundreds of variables together, right? So if you want to do a useful anomaly detection, we need to understand that to this anomaly to evolve, what are other anomalies happening into the process, and which parameters are changing around and causing these anomalies. So basically, it's becomes a multivariate problem where we look at a plant, process, or asset holistically, and then try to find that what is wrong going about it. So if you look at what are the methods available for doing these kind of anomaly detection, process anomaly detection. So very much is visual and rule based. So we have seen that univariate time series, and instantly anybody can look into it and tell where the anomaly is. So the similar visual based graphical tools could be looked upon, and then anomalies could be identified. These are easy to implement, and also you could write some rules to do these detections. So these are easy to do, easy to implement, but the problem is once the number of variables increase, it becomes extremely hard to look into hundreds of variables and write rules for all the possible interactions happening into those variables, and also distinguish them and find where this particular anomaly is happening. So beyond few variables, it becomes not a feasible solution. And next could be physics-based process model, and we all know we could build a kind of simulation model using first principles. We talked about all those partial differential equations, thermodynamics, and these models are efficient. They work good. They mimic the process behavior very well. But as we know that complexity keeps increasing as we want to do more details. You need a lot of inputs, thermophysical properties and all, and again it becomes computationally expensive. So not suited for real-time analysis, this one as well. But you could identify problems and explain them, fix them much easier than any of the methods if you are doing it physics-based approach. So next is AI-based, and we talked about some of the basics of AI, and of course the AI-based models could do nonlinear interaction modeling, and with good compute power available, we could do quick training and implementation. Inference is even much faster in this case, so it could run in real time, highly scalable. So you build for one system and you could very quickly take it and train for another similar system, so and deploy it. So you could scale it from one plant to another plant, and of course we have data processing, and you could run it real time. But there are some disadvantages as well, and we'll examine on the next slide, and also we look into how we could go past it to build a better process anomaly detection system. So so how AI methods, what are kind of AI methods are available to do the process anomaly detection? And we talked about these unsupervised methods early, where we give the data to AI models and they learn about it. So for example, here you just dump all these data and tell AI model that you learn about this data and tell me where the anomaly is, and most likely it will find the right ones. The second way of doing is we call semi-supervised. So earlier we only covered unsupervised and supervised, but there's an intermediate category, we call it semi-supervised, and where model is trained on normal behavior. So and it is also known as novelty detection. So here you take a process or asset and see that the period where it is running good, and then give it to AI model to learn about it. So it learns its good behavior, good process behavior, where your performance is good, your product quality is good, there is no problems overall in the running the process. So in that condition, the AI algorithms learns that how a normal process works, and once there is any deviation to it, it will detect it and notify. So if you want to train a semi-supervised algorithm, you'll remove this anomalous data upfront and give the remaining good data for it to learn. So it will learn this baseline of operations, and then these kind of spikes, once happens, it will detect it. And there are many methods to do it. So I have listed a few of them. And then the other method is supervised. And here you need to classify observation as anomalous or non-anomalous in nature. And to train it, you have to level each and every point of your data as a 0 and 1. So basically 0 is non-anomalous and 1 is anomalous. So you see here, you are doing a lot of work. So upfront, you have to go and put a label to each and every data points, and that's a lot of work upfront. So that's why in anomaly detection, supervised methods becomes very tedious and not easy to implement. And you see the risk with unsupervised, that you don't know how it is going to learn, and probably it might find something non-anomalous, which is actually anomalous. Or it will find something anomalous, which is not anomalous. So that risk always you have, and you have to do a lot of tuning to figure out a right model here. But the middle path is semi-supervised, where you are exactly telling the models to learn the normal behavior, and that's where it gets it and mimics it, and then now if anything goes beyond that normal, it will highlight as abnormal or anomaly. So that's the most efficient, and also it's scalable, because you're not doing a lot of manual work of leveling the data. You have to just remove certain periods of data where process was not anomalous. So this was some background about different methods available for doing anomaly detection. So now we earlier talked about some problems with the anomaly detection algorithm. So if you take out-of-box anomaly detection algorithm and apply it, most likely it will do your anomaly detection part right. So it will be able to see that, okay, see your this particular point is anomalous, and that detection is successful. But that's not enough. Means you just know that my process is anomalous, and what you are going to do about it. You need to understand what is going wrong, and then what can be done about it. So what caused that anomaly, whether it was a pressure drop, column pressure drop, or there's a foaming happening into that column, or there is a rise in exchanger outlet temperature. So we need to understand it, and generic algorithms cannot give you this. It's more like a black box. So you got to know that I detected anomaly, and then that's where it stops. But without knowing that why it is happening, you can't do much about fixing the problem. And if you do not know what is causing that anomaly, then we also can't take any action. So whether if it is foaming problem, then you could do anti-foam addition. If it is exchanger outlet temperature rise, then probably exchanger is fault and you need to clean it. So those kind of actions only could be done only if you know the second step. And again, that would be missing if you do a AI based model without just a kind of a black box AI model. So what is solution? And solution is doing an explainable AI and then adding domain knowledge along with it. So let's understand how this works. So when we call it explainable AI, so once these methods, once the anomalous process detected, they also give contributing parameters. So it tell exactly that which are measurements, which sensors particularly cause this particular anomaly. So you can localize that problem. You'll able to understand, okay, this is my inlet temperature, or this is outlet temperature, or this particular pressure. So you know 3 or 4 top parameters causing this anomaly. And once you have that knowledge from AI models, uh, you could have a digitalized domain knowledge, because as we work in this industry, and we know there are certain kind of problems happens, and these are the way to solve them, and all those knowledge is available with us. So the next thing we have to do is take those knowledge from our experts and digitalize it in a format, a digital format, which could work with this AI system together. And so once we know this, this system kicks in, and it could be a rule engine based on the tribal knowledge gathered over a long period, or for example, say for you were looking into the process or assets, you could create a kind of failure mode effect analysis, maybe slightly different than what usually done in the industry, such that it could work with the software or automated process. And with consuming this information, it produces the prescriptive output. So the 2 steps what we were missing earlier, it is going to fill that. So we got contributing parameters, what is causing it, and based on it, this domain knowledge can give us what is probable cause. And once we know the probable cause, we could also guide it to what kind of action needs to be taken to fix the problem. So that's how this whole system could be enhanced to be useful in industrial domain, by combining, making AI system not a black box, but explainable, and augmenting with the domain expertise. So now let us see all these together as a architecture, that if you want to set up this kind of system, how it is going to work for a process. So here we have a, say we take any process or asset, and we have some measurements available, sensors data available, and we start from there, and then we go and do a feature selection. Feature selection is basically identify parameters which are important for a particular objective you are looking at. So here again, the domain knowledge comes into picture. We already know by physics which are the important parameters. So that should be a primary criteria for choosing which are the tags we are going to use into this model, based on the domain expertise, process expertise, what we have. And there are methods also in data science to identify, and of course we should validate with those methods our physics understanding. And once the both are in sync, we identify those parameters and then proceed. And we take the historical data and remove the anomalous period. So we call it like normal historical data. That is the approach, semi-supervised approach previously I described. And then you train this anomaly detection model. And once you do that, then you have a trained model available, and that trained model could run online. So you could push in live data to this model. It goes through a data pre-processing, and then trained model scores on that data. And output would be explainable output, where you will see a composite score saying that it is anomalous or not anomalous, and contributing parameters as we saw in the previous solution. And once you have this information, you can feed it to a domain knowledge base prescriptive engine which could give you causes and recommendations. So that's how the architecture of this kind of solution can be put together and deployed into the production. Okay, so now we have covered some basic fundamental about anomaly detection. So we get into a real use case where this is being applied, and we'll try to understand that how it works with example. So the application is in an ammonia plant, and as all of you know that ammonia plant takes natural gas and naphtha as feedstock, and that goes through desulfurization, and then it goes into reforming process where you make a hydrogen, which is a key ingredient for synthesis of ammonia. So this reforming process also produces a lot of carbon dioxide and carbon monoxide. And the ammonia synthesis catalyst, CO2 and CO are poison to that catalyst. So they have to be removed completely from the system before this raw gas, which contains hydrogen and nitrogen, comes to the reactor. And to do that, we have a system here, CO2 removal and methanation process. And the whole objective of this system is to remove CO2 from incoming raw gas, such that you could avoid poisoning of the catalyst in ammonia synthesis reactor. And if there is a situation that the system is not working well and there is a high amount of CO2 escaping from the system, then is the trip system, which goes and trips whole plant, because you don't want to deactivate the catalyst and poison it completely. So the high excursion of CO2 could cause a whole plant shutdown, and you know that is cost of a plant shutdown. You need 3-4 days to bring it up, and there's $1 million lost into plant profitability. So what we want to do is we want to detect this anomaly, and we want to detect it upfront, why it is happening, and then what can be done about it. So that's kind of solutions we're looking into for this use case. And this is a process flow diagram of removal system, and this works as is a CO2 absorber, and this is amine-based absorption system where you pass amine from one side, and the gases are going upward. Amine is coming counter current, and then as we know, amine has affinity to CO2, and it's get absorbed. CO2 get absorbed on amine, and finally that amine goes to a stripper, and it releases all CO2 and come back, recycle back to the system. So that's the very high level operating of this plant, this particular subunit, which removes CO2 from incoming gas. So already we discussed this. The objective is to predict anomaly before excursion event, because we want to eliminate it. We want to take some action such that this does not happen. And of course, it should be a prescriptive where you could do possible causes and do a recommendation. So again, the same architecture what we discussed before. So you start with the whole process data, then you select a few which are important for the excursion events. You remove the excursion events from historical data, train the model, and then once the model is trained, you go live and start running it on real-time data to pick up these anomalies as they develop on the go. So when it is running online, this is an example I'll be showing, and you could see there is an excursion here, CO2 excursion. The values are going high, and it is happened around 7 a.m. Time. Now, these are the results from AI model. We call it anomaly score, and you could see a threshold here, the black curve. And once the scores goes above the anomaly score, then we call it that system is getting anomalous. And now you could very clearly see that anomalies started happening around 4 a.m. So the excursion event happened at 7 a.m., but we have anomaly build started much early, 3 hours early to this event at 4 a.m. itself, and is kind of on and off the start, and then they kind of stabilized. So next, we talked about contributing factors. That is next part of explainable AI. So we also want to understand when these anomalies happened, what caused it. So which are the parameters of that whole CO2 system is causing these anomalies. And if you look closely, these are mostly the temperatures. Flash bottom temperature, cooling water supply temperature, absorber inlet temperature. So these are the parameters which are mostly driving these anomalies in this system. So now question comes here that how did AI system is able to pick up anomalies much before the actual event? And we'll understand it in next few slides. So again, we'll come back to the process flow diagram of the CO2 system. And you see a lot of exchanges here, and the objective of these exchanges to cool the amine, because we know the absorption process is sensitive to temperature, right? And if temperature is high, the absorption is not going to be good on amine. So and stripping is being done by raising the temperature. There's a reboiler here. So the lean amine which comes out after a stripper, it is always a high temperature, and then we utilize cooling water exchangers to cool that amine such that it has a lower temperature to absorb again incoming amine thing. So we have a cooling water system also, which is very much upstream of this process, which is sending required water to cool the amine to reduce the temperature, and also it is being used to and then basically this cooling water coolers, they utilize the seawater as a coolant in this particular case. So let's look next about our contributing factors, which we were looking into, and these are HP flash bottom temperature, and that is here, HP flash bottom temperature, and you could see the measured here, and then absorber inlet temperature, which is just measured below absorber, and then we had this cooling water inlet temperature, which is measured very much upstream of the whole process. So just to understand that where these measurements are on the flow sheet, to understand why we are able to detect the anomalies upfront. So now let's look into the time series chart of these parameters. So this is the actual anomaly. This is output when CO2 ppm we are measuring, and it start to go high. And if you are like very attentive and just staring your screen all the time, this is the screen, probably you'll able to see some noticeable change or upward movement on the CO2 ppm. That would be like 6 a.m. So, but if you look at these contributing parameters, and if you want to do the same, you'll be able to see the upward movement even like almost 2 hours before, around 3:30 a.m. itself. And same is true with the HP flash bottom temperature as well. So you could able to see this much early, and this is happening because there's always a lag in the process. So these parameters are getting impacted first. So the problem is occurring here first before it is exhibiting on the CO2 ppm, which is basically output from the system. And if you go further upstream, the another parameter we had like cooling water supply temperature, you'll be able to see the excursion happening here much early. It is 2 a.m. So more and more these parameters are upstream. We have more and more lead time, or basically we could detect them early. And that's why we were able to see the anomaly scores going high at very very much before the actual event happened. So basically contributing factors or precursors started to change much before the actual CO2 excursion. And that's the idea of detecting it much early and then fixing the problem. So now how if you put all these things together, on a prescription engine, which is a domain based knowledge and FMEA, and you can put it together to a certain causes and issues advisory. So here we had contributing parameters, which were cooling water temperature and amine temperature. So we know there is some problem with cooling water, and that is driving the whole system. The temperatures are going high, and temperatures goes high, then your absorption is not going to be good, and then there will be excursion into the output CO2. So a prescription engine is based on domain knowledge. So we know all this, how whole dynamics work. So if cooling water temperature is high, the causes could be either you have reduced cooling water flow, or also this could happen because increased raw gas temperature as well, because that also comes in those heat exchangers fluid downstream. And what can be done about it? Because operators might have few handles, and if this is the situation, then the engine, what we put based on physics, it could recommend whether you increase the seawater flow, and if that is not the possibility, then we could increase the amine flow such that absorption, we could absorb more CO2 and eliminate this process. And once those recommendations applied, then the process can be controlled, and it could come back to normalcy here, as we see. So this was the one use case about ammonia manufacturing unit, where anomaly detection is being used. Now I'll cover another use case, and this one is for process optimization of direct reduced iron (DRI) process, and this is from steel industry, but it's very relevant chemical engineering, so that's why I thought to include it. So we'll cover here a brief intro of DRI process. So if you are not aware, I'll just cover the basics so you could follow the presentation, next presentation, and then what kind of artificial intelligence and applications are being done in this particular case. So direct reduced iron process objective is to reduce the iron oxide, hematite and magnetite. As we know, the ore remains to a metallic iron. So and it is being done in a reactor. So you could see here a kiln in this process flow diagram, and this is a rotating high temperature long reactor, which is being used to do this reduction of oxides to metallic iron. So feed to this kiln reactor is iron ore pellets. So iron ore pellets, these ores, oxides, what we have, it is being pelletized up front and feed as a from the front end of the kiln. And then we need a reducing agent as well, and then also a heat source, because this is high temperature reactor. So the heat source is also coal. So coal is being burned in this kiln to provide the heat source, and also carbon present in this coal act as a reducing agent. So coal serves both purposes, heat source as well as the reducing agent. And of course, if you want to do combustion here and raise the temperature, then you need some combustion air as well, and that is done by air. And air is being supplied from rear end, that is a primary air, through a fan. And there are air tubes on the kiln which supply the secondary air as well. So as you could see here. And the final product is a reduced metallic iron from this process. So what you see downstream is all like cooler, which is being cooling the final product, and then all this separation process. And then upstream is, since this is high temperature kiln, a lot of gases, high temperature gases are coming out. So you need a waste heat recovery system, which ultimately runs a small power plant to produce power. So, but our main focus is the reactor, the kiln here, how we could optimize it better performance. And a better performance means you keep the throughput as high as possible, and meet the reduction target. So you want to reduce 80% reduction you want to achieve. So you try to keep it as high as possible, because that's what drives the market price of the product. So if we have better reduction, you could sell it at higher price, higher grade of the product. So that's the overall objective. So if you look at the parameters which are impacting overall reduction, which is our criteria, and this is phase diagram of iron oxide reduction, and very clearly you could see that high temperature is favoring the reduction process. So you want to keep the temperature high such that reduction happens better. But also high temperature causes accretion of fusion of the ash particles present into the coal, and they get deposited on the surface of the kiln, and they inhibit the flow. So you don't want those accretion rings to form. So temperature also cannot go very high to that to happen. So it's like becomes a very optimization problem where you want to keep it within a range. And if you look at the kiln retention time and reduction, and it's very obvious, you put a material longer in the reactor and give it more time for reduction, then of course you are getting a higher reduction. But increasing retention time also reduces the overall throughput, right? Because you're keeping a material longer in the reactor itself. So there should be a good balance on the kiln retention time as well. And then the last and very important one is availability of carbon and oxygen, because you see here that reactions, carbon is a reducing agent, and basically carbon monoxide here is a reducing agent in these all reactions. And if carbon and oxygen is not available throughout the kiln in very optimized way, these reactions are not going to be even throughout the kiln, and then we are going to have problem. And you see these kilns are like almost 100-meter long. It's not a small reactor. So a lower carbon to iron ratio will cause lower reduction. So if we are feeding less coal than required, of course, we are not going to achieve it. And if you put more carbon also, again, that is not nice, because you'll have problem with the temperature control. You'll have problem with also you are spending unnecessary more coal. So basically, if you want to improve overall process, and efficient temperature control and uniform carbon distribution is very much needed to do it. So now we look into that. What are the what are the challenges and problems with this particular reactor? So this is again a schematic of the kiln, and you see this preheater. Before that, ore feed coal dolomite is being added to reduce sulfur, which is undesirable component. So that's the objective of it. It is being fed to the kiln, and we have also you see that the injection coal is being fed for the rear end, and objective of sending the injection coal from this end, because the feed coal is getting consumed by middle of the kiln. So whatever we are putting along with the iron ore, it get consumed once material reaches somewhere in the middle of the kiln. So for second half, you need to also have a reducing agent and a combustion aid to be put in, and that's being done by injecting or throwing coal from the rear end of the kiln. And when we are throwing the throwing the coal, we also want to ensure that there will be good distribution. So while throwing it, some material falls evenly at the rear end, as well as it goes through the middle of the kiln as well. And that's why they put a mixture of coarse coal and fine coal, such that distribution remains even at the second half of the kiln as well. So now let's see what are the temperature measurements available on the kiln, because we saw that temperature is very important parameter driving the reactions, and as well as if it goes out of bound, it will create some problems as well. So they have these thermocouples installed in this process. So in this process, we have thermocouples which are inserted inside, and they do a real-time measurement of the kiln temperature in different zones. And here the air tubes are also installed, which could inject air inside the kiln and that particular zone. And there is a primary air which is being fed from at this end. And the another temperature measurement is manual, that is called quick response temperature, and this is being done by manually inserting a thermocouple inside the kiln, and it is done infrequently. So every 4 hour to 6 hour, manually somebody goes here and then they insert the thermocouple inside, and then they take a temperature measurement.
शांति होगो, शांति करो, भूल जाओ, भूल जाओ, भूल जाओ.
Is there any question? Okay. So the problem with this NRT continuous sensors is since we are doing this whole particles are being having as particles into it, then they get deposited on the thermocouples, and then this continuous measurements becomes inaccurate, and that's why they take this manual measurement, so which is done manually. So these are the two sensors available, and temperature control options. We have primary and secondary airflow. So of course we could increase or decrease the air to aid combustion or reduce combustion, and of course the coal itself. So how much feed coal or the injection coal you are putting, these are the some options are available to do the temperature control. And challenges, as we discussed, the unreliable NRT temp measurement, and that is due to the coating happening on those thermocouples, and these QRTs are intermittent, so they are not continuous. You get every 6 hours, so you don't know what is happening in between if your NRT sensor is not working properly. And another challenge is air profile management. So these are if air profile is not nice, then temperatures are not going to be even throughout the kiln.
Yeah.
So if you look at carbon control, another thing we talked about carbon control, right? So we need a very uniform distribution of carbon across the kiln, and that is being done using fine balance of coarse and fine shear, and that needs to be very much balanced, and feed coal set points. And challenges with carbon control is the fixed carbon, moisture, volatile matter, and all keep changing into this coal which is being injected. So your effective carbon also changes if the fixed carbon of your coal changes. So that needs a change into the set point of this coarse coal and fine coal here. And also particle size variations happen. So if particle size changes, then you also have to balance coarse and fine coal such that even distribution can be maintained on the second half of the kiln. So these are the challenges with temperature and carbon control. Now, very quickly, we'll look into artificial intelligence and its application in this particular case. So to do performance optimization, we have seen a problem that you could not get a reliable kiln zone temperature because the continuous sensors get coated with carbon particles and then as particles, and then the QRT measurement, which is manual, are infrequent. So we need something which a model which could give us a reliable kiln temperature zone measurement. And another item to optimize the whole process is of forecasting the product grade. So we are looking at how much reduction is happening when material is going out, and this measurement is done in a lab. So the samples are taken to lab, and every 2 hours you get a measurement of from lab that how much reduction actually happening. And this is slow process. So whatever action you take, it take long time to exhibit. The material remains in kiln for almost 16 hours. So any action taken will take some time to have impact. So you'll keep producing off spec for some time. So that's why the forecasting the grade upfront to understand that next 8 hours how my grade is going to be. If you can do that, then these actions could be taken upfront, and then overall plant grade could be improved. And then optimize set point recommendations for cold feed, that includes fines and coarse, because there is variation in particle size, there is a variation in fixed carbon moisture in the coal. So based on those, these optimized set points could be given. Of course, the overfeed, so that would help the optimal throughput through the system, and all these primary and secondary recommendations such that we keep the whole temperature profile of the kiln stable. And then the some monitoring part where we look into the overall anomaly detection of kiln process. So here you take all the variables together and then monitor the kiln for any deviation happening. And of course, means we can create a lot of health scores on key performance indicator, which could be monitored for overall process. So these are some very high level applications we have done. And very quickly, I'll show in next 10 minutes how it look like. So continuous QRT forecast. So we talked about this. NRT measurements are normal response measurements are continuous but not reliable, and QRT is intermittent. So now all these intermediate operations run on the guess value. So based on operators' experience, they change things in this case. So we could do a kind of model, and this is a regression model, soft sensing model, which utilizes these manual measurements as well as these continuous measurements, which are not accurate or may not be accurate, together to have a more robust real-time measurement of kiln temperatures. And also we could forecast them in 30 minutes to 1 hour in future, how they are going to evolve. So these models gives us more robust results. So this is one of the example what you could see. Actual NRT is measuring 200 degrees C, but that's not possible because the whole kiln temperature remains more than 900 degrees centigrade. So definitely there has been some severe coating happened on it. But once we take this data, but still this sensor is sensing the variations. So relative variations are being captured by this sensor. So it has useful information with it. So we take this data and manual measurements, and then we develop a AI model which predicts real time of these NRT temperatures. And when we validated, it was pretty close to the actual measurements. So the next was product FEM forecast, and that is as we discussed. So we do forecast the product grade 8 hours in future, and for this this is the very high level architecture. Because of time constraint, I'll not go through all of it, but it was a deep learning model, a neural network model, which is being used to do this forecasting of FEM. And these are some results what you are seeing, where actual FEM values you could see, and then forecasted values you could see, which are 8 hours in future. And we look into what was the accuracy of whole model, what was the gap between predicted and actual, with some tolerance. So you could see these numbers, and mostly the directional accuracy was very accurate. So whenever the model is predicting that grade is going to drop, it is always going to drop. But if you look at absolute accuracy, how much it will drop, there will be some differences, and these are error trends what we are seeing on the chart here. So next is a optimized fines and coarse coal advisory. And in this case, you see this coal particle size. So here you see a variation. So coal size is high and then suddenly it dropped, right? And also you could see fixed carbons. Fixed carbon is oscillating around like 56 or something, and then there has been a drop in fixed carbon. So these kind of variations keeps happening in the coal quality, and if it happens, then we need to change the set points of overall coal. So AI model identify the best operating condition based on historical data. So understand that what should be the ideal distribution of coal particle and how much carbon is needed. So one thing is you could calculate through a stoichiometry and some thumb rule what plant had, how much carbon is needed, but also you could look into the historical data to extract out the good operating regimes to understand what works best. And then that becomes a model for deciding how much carbon should be, how much coal should be fed, and then also how particle size distribution should be. So once we have those information available with us, then that could help us to do an optimized estimation of coal set points. So both feed coal as well as injection coal quality also. So here you could see the recommended coarse coal and fines coal, and you see means overall you want to keep total carbon constant, but since there are variations in the particle size, you want to keep changing the coarse coal and fines coal ratio such that we final mixture of injection coal, which is a combination of coarse and fines, remains same in terms of particle size distribution, such that you have very good even distribution throughout the kiln. And same goes with primary and secondary air. So the current set points you could see, and then if there is a requirement we need to cut air, there is here is a recommended ones, and the one on the kiln surface were controlled by dampeners, and then you could see the similar recommendations by changing the dampener notch such that we could control the secondary air also to have very optimal temperature overall on the kiln surface. And finally, the monitoring part, what we are talking about, the kiln process anomaly detection. So we again, this is very similar to one we talked before in the ammonia manufacturing. So you take a data, normal operating data, when the reduction is above 80%, which is a minimum target to be achieved, and all other parameters are optimal, train the model, and then analyze in real time for abnormality from those ideal behavior on which model is being trained. And once it detects any abnormality, it does generate alerts, and also does least probable cause in action, which is being built on the basis of domain knowledge. So here is an example of anomaly detection. So you see anomaly score being below threshold, and at this point, this particular point, you see there is an abnormality detected. And once we inspect this area, we will be able to see what are the abnormal parameters. In this case, it's fines mean particle size. So there's been reduction into the particle size of the fines. And if you can inspect the time chart, and you could see very clearly that there is a dip into the mean particle size, and that is causing this anomaly. And once we have this information, next could be done is a alert, cause, and recommendation, and this could give a cause. Maybe there has been issue maintaining a FEM, right? So that is a product quality maintenance problem, something it is identifying, and also seeing that there is a particle size problem, particle size distribution problem, and some recommendations could be issued based on these causes. And again, these are being based on the domain expertise and domain knowledge. So now we come to the end of the presentation, and before we wrap it up, I would like to so very high level overview. How do we operationalize AI solution, right? So in an industrial setup, so we have a manufacturing plant, and we have assets and processes where all the data is being historized, either historians or some database or DCS systems. So we can connect with those, take the data, pre-process it. So pre-processing includes all kind of cleaning of data such that it becomes useful and ready to use into the analytics. And as we looked into the only AI or machine learning kind of models are not going to work, but you need to combine them with physics, thermodynamics, as well as domain expertise, rule systems together to have a reasonable and useful solution. And finally, results of these would be, if there is some problems detected, it will alert it or forecast certain parameters, and then give some prescriptions about it. And again, we need to feed back all these findings based on how user analyze. So these systems has to be self-learning. They has to be keep updated based on user feedback, and they can keep evolving as we go. So now, finally, at the end of presentation, I would like to put together what is the really required component of a successful artificial intelligence intelligence solution. And we start with data science. Of course, you want to analyze data and build models, but you should never forget domain knowledge, because without that, it is not going to be successful. And then the third one, business strategy is very important at very starting of the project itself. So we need to also think about value creation. Means it's not be only technology driven; it should be business driven to be successful. And once we have these domain knowledge, data science, and business strategy together, define a problem and a solution. To make it operational, you need data engineering, which is mostly about software and infrastructure part. And once we put that together, we also need to drive the change management. And usually this is being ignored, because this is new technology, and always there is a inertia among people to use new technology. We think that, okay, I have to learn something new. I don't know what it's all about. And everybody is afraid who has not seen this before, and they think it might increase my overall work. So we need to train people on all these and make them understand that this is going to make your job easy, not difficult. And overall, these AI systems are not going to replace any worker in industrial, means what we are looking at. It's more like an enabler. It helping operator to focus on more intellectual task, and do some most mundane data crunching and give insights to operators. It's more like a co-pilot, right? So it's not going to displace jobs of operation team. So that is one has to be communicated very well with the team to gain their trust and support, and also train them on these technologies so they start feeling comfortable using it and applying it. So these are some real important aspects what we have to do to a successful artificial intelligence solution. And also we see that this is not like one domain, but it's multidisciplinary approach, and you need a good team working together, collaborative way to make it successful. So this is here. I will stop my presentation, and we can be open for Q&A session. Thank you.
Thank you, Sudhanshu. Excellent session. We had a lot of takeaways. I'm sure there'll be a lot of questions which will be put forward to you. A very engaging session. Now we'll keep the forum open for question and answers. Participants, you may please unmute and ask your questions, please.
Hello. Hello.
Yeah, go on, Rahul.
Rahul here, sir. So first of all, thank you for arranging this wonderful session, right? So I have some question like, as Sudhanshu sir told about the threshold in anomaly detection. So how we will ensure the how we will get the threshold limit? So is there any specific formula for that?
No, it's not formula. Basically, the way you are training the models. So when we as I explained, we take normal historical data to train the model. So model understand that what is the normal behavior, and AI algorithm, machine learning algorithm itself will decide what will be the threshold. So you don't have to specify those limits by yourself. So leave it to a model to figure it out. So what you can control, that you always give a good data for it to learn, and on the basis of it, it will learn those boundaries.
Okay, okay. So one more question, like suppose you told about the anomaly detection. In that you shown some multiple algorithm. So is there any criteria to which time we have to go for the particular algorithm? Like you are saying Kn and random forest and all this thing you mentioned. Na? So how we
Yeah.
will decide which time we have to use that particular algorithm?
Yeah, so there is no straight answer to it. You need to try it out. So you could try it out one algorithm, two algorithms, and sometimes there's an ensemble of algorithms work better. So instead of doing only one algorithm, you do apply three algorithm and then take a final result, a kind of weighted average, or some kind of weightings you can do, and that will give you much stable result compared to the one algorithm itself. So one problem with machine learning, upfront you cannot tell that these kind of methods are gonna work. Based on experience, we have some selected algorithms, but it is no guarantee that for a given problem one will work all the time. So it's more about trial and error, what you do, and then find out which one giving you the best result, and then you go with it.
Okay, I will get it.
That's what
So
data science exploration.
so you want to say like we have to run all the model and we have to compare which gives us more accurate value, right?
Yeah. I mean, so you don't have to run all the models, but you can, based on some intuitions, you could select few upfront, and then maybe you could try three or four and see which one is working best.
Okay. Okay. One more last question for me. Like, suppose you said about for the heat exchanger fouling, right?
Yeah.
So suppose I made some model, so I trained and it's give very good prediction. After that, the most thing is like when we do automate that particular model. So suppose we are getting some values, live values from server, like we have suppose getting from SQL server. So that time, how we will get automated all this thing in a one like one code. So can you give some information about that?
Yeah. So as I explained a few slides back, you need to make a live data connection to your program and the plant historians. So such that you could fetch the data in real time, right? So for you have created your fouling model which you want to run it real time. So you also need data in real time. And say your plant has OSI-PI or IP21, those kind of historians where data resides. You need a certain, and they allow certain protocol. Using that, you could get data out of them and then use into your analytics. So you need to write those some bridge code or connector code to get data in your program.
Actually, what happened? Sometime we have some selected some text, but at the same time, the all value is not coming, right? So there is some issue. Like we suppose for particular data prediction or whatever thing, we have to need some exact value at the same time. But in a our case, is problem is that like there is a no specific time value. So that is the issue for me.
Yeah. So that is very common issue, and that's where the pre-processing part comes into picture. So you need to take data and harmonize it, and if needed, you could interpolate data in between for your models, or you could say certain data has a low frequency, right? So you might get one data every 5 minutes, another data you are getting every 1 minute. Then
Yes.
you could keep that 5-minute data frequency, it's constant for 5 minutes until you get new data point, and then
Yes.
use it together. So these are some techniques you could put in data pre-processing part before sending it to any analytics you are deploying.
Okay. Thank you very
Yeah,
much.
Shankar, please go on, Shankar.
Yeah, Sudhanshu, I've been in this chemical engineering field for the last 51 years. Just wanted to see where this artificial intelligence is going to take over the running of process plants, continuous process plants in India. And where do we see, what is the timeline? And what is the education and training requirement towards this goal in India happening at the moment? Because the two examples that you gave, they are all, I believe, for the plants which are abroad. And they have been working on AI-based process control for several years, at least 15 years, as I can remember, whether 5G or not 5G. So what is your take on this? Yeah.
Yeah, so of course, means India industries are a bit behind. If you look at AI implementation and openness to AI as we go into market, but now we are seeing a traction. And one major difference what we see in India market and European and US market is in India, everybody wants to use a very well-established solution, and AI is not at that stage. I mean, even globally, if you see, it's in infancy, and you are trying many things experimental, and many of these use cases are unique, the first in that particular kind of industry, right? So there needs to be certain experimentations, and of course, with each and every experimentations, there is a risk of failure, right? So we need to go through that cycle, and I would say maybe next 5 year India market also will be more receptive to these changes, and maybe overall it might take a decade to become a kind of mature product line. What works, what doesn't work, what kind of solutions brings value. So a little bit time is there, but we should start trying it out, and these technologies. And second question about training requirement, and of course the what I would recommend that we start with our users. Those are, for example, say process engineers or plant operators who are doing day-to-day activities, and all these young folks joining, they should get some knowledge of data analysis, data understanding, and do informed decisions. And there are a lot of courses available now online. You could do it. You don't have to enroll to university as a Coursera or these kind of courses are available, and it's not very costly also. Or you could find a lot of content on YouTube itself to get yourself trained. So I think that barrier is very less, training barrier. If somebody has will, they could get trained very easily in these technologies. And also it doesn't take very long to get started. Maybe a year of effort will get you kind of up and running.
This is Murthy here. Adding to Sudhanshu's reply, in India itself, no, the entire Tata Group, no, Tata Power has gone for in AI-based complete set point optimization with the predictive analytics. There are 3 plants running with the totally on AI model. Reliance Jamnagar refinery for few of the units, no, they implemented with AI model from different vendors. And the NTPC, at least 4 or 5 plants, they have gone with the AI model based both prediction and predictive analytics as well as closed loop optimization. And most of the cement plants in India, they are ahead now in this. No, they have gone the APC earlier, again refineries and power plants. They also gone AI-based model. You take right from Ramco Cements to India Cements to Zuari, Aditya, you take Gujarat Ambuja. Anyway, it's a Lafarge. All companies have gone for that. So the adoption of going for AI-based model is pretty popular in India as well. The only one problem is they are not going for a cloud environment. So the adoption of cloud, you know, all these systems going to run on a cloud. The only issue in India, no, they are not still coming forward to run it on a cloud. Most of them, they want it in non-premise. That is the only issue. Otherwise, no, India also so much adapting in line with abroad. This is another view, no, where at least I have been involved in 7 or 8 implementation with these Indian companies as well. Yeah,
Yeah,
so
but Murthy, advanced process control and multivariable process control, they have been there for a long time.
no,
But
I'm not telling about. I'm not telling about.
this is
No, one
what
minute.
the example what you gave
Shankar,
are those.
Shankar, that's what I'm
Hmm.
saying. No, APC is there for a long time in refinery.
Yeah, that's what I'm saying.
First, I'm telling about. That's the reason I'm telling you. APC was there in refineries very earlier. Cement plant it's earlier. This AI-based model control, whatever no, this gentleman talk about no from Symphony. There are similar products available, including Symphony, GE products, and then Invensys, Symphony. There are around 6 or 7 popular products in the market. This has been implemented by Indian power plants, Indian refineries, Indian cement plants, and is in operation for the last 3 or 4 years. There were pilot. Now this pilot has been converted into a full implementation. You can talk to me one-on-one, and I will tell you know which plant is in operation, what are all the benefits they are getting it. I will share you. So I was part of complete Tata Power, no, the entire AI based, whatever no the Sudhanshu spoke about, they have implemented, of course, in a different way, but it's totally on a AI based model. So the point what I am bringing now, India, it's also bringing all these technologies. Yeah. Only they are not bringing the cloud. That's the answer.
Yeah, the traction is happening as Murthy sir explained. Means we are seeing quite traction. We are talking to many companies nowadays in India, and they are interested. Means they want to try out. Yeah, means of course it's early stage, but means we are getting into.
Yeah, Ramesh, go on, Ramesh.
Thank you, sir. Hello, can you hear me?
Yeah, go on.
Yeah, it's a wonderful presentation. Thank you, Sudhanshu, really taking us through right from the basic all the way up to how we are giving a solution to a customer. So I got a couple of questions on it. One is that I know finally on the heat exchanger problem on the ammonia plant, you mentioned that there is a cooling water flow issue. We're able to figure it out because the temperature low and all. So how are you doing that mapping of the different parameters? Like, are you already mapping like what are the causal variables or dependent variables, or your model goes and, culls out of the 1,000 variables, okay, this is what causing it? And that is my first question.
Yeah. So the model, the explainable AI, what I mentioned, it does predict anomalies, and also it tells why it is happening. So it gives us those parameters which are causing it, and also means how what is the relative contribution to that anomaly. So that information we get from models itself. And the second part where we figure out what exactly going wrong, that's where we create, as you mentioned, the kind of templates, all these FMEA kind of templates where we could associate causes with those sensors where problems are happening. And that mapping we do often based on domain knowledge, and it is digitized and uploaded to run in real-time automated manner, and it picks up based on AI results. It goes and looks into those templates and find a right cause, and then does a recommendation along with it.
Yeah, thank you. Yeah, that's wonderful. This just on to that earlier question. So what do you see the difference between this APC methodology or versus this AI methodology, which we are now heading towards? Yeah. How much is this different, and can you elaborate on that? Yeah.
Yes, so it's a lot different. Means there's a APC. The way APC was working is you do kind of all this test, right? Where you do a step test and try to find that how these variables impact each other, and then build some very linear model and do kind of very short-term forecast. Means maybe 10 seconds, 5 seconds, because we see all the our problems in chemical engineering, industrial, they're all non-linear in nature, but APC models simplify those by making the time horizon short and creating a short time forecast. and then do very quick control over it. So here with AI models, we get a better handle on that. We don't have to go for short time forecast, but you could do a longer period forecast, because AI models with given good amount of data to learn from, it could model the non-linearity of the system and do a long horizon forecast. So basically, you could do a better process control compared to the APC, and also you could put it for some systems which are very slow, right? Where dynamics is slow, and you could control it better. So that's one major difference from APC to AI systems, and of course means application of AI, and that is about only about the process control part I'm talking about. But if you look at the other applications like forecasting certain parameter, or detecting anomaly detection, doing soft sensing, those are completely new applications which APC was not solving before.
Mr.
Okay,
Rajendra,
thank you.
please.
Thank you.
Yeah, Mr. Rajendra, go ahead.
Thank you. Yeah. Okay. Sudhanshu, first of all, a very nice presentation. The topic is complex, but you explained it quite nicely. One question I have is you mentioned about semi-supervised learning. So is it basically a different algorithm, or is it mostly you are actually selecting the data so as to provide only the normal segments of the time series and training the model?
Yeah, it's that only. So many algorithms can be tweaked to work that way. So difference is the way you do the training, where we are giving normal data to train the model. Yeah.
So you're selecting all the normal portions of the model, and if anything comes up which is not normal, that will be detected as an anomaly. That's what you're.
That's correct. That's correct.
Okay, great. There was another question that I remember that there are certain DCSs which have like fuzzy controls, or actually fuzzy neural control and all that. Is it in similar, or is it in contrast with the kind of techniques which you are actually presenting here?
Yeah, fuzzy logics are being there for a very long time, and then it is very much being used into this process controls. But these methods are different than fuzzy logic, because there you build some rules and try to implement it in the system. And the machine learning, the major difference, you don't tell it any rules. So machine learning does figure it out from data. So that's the differentiate from the previous generation AI systems like rule-based fuzzy logic and all, compared to the advanced machine learning algorithms what we have. So that's the basic difference we see here. And more and more data you can give, better and better it can learn. And the limitation with rules, that you could write limited rules, maybe 50, 100 and all, and then it becomes very complex, right? But with machine learning, it is like you don't have to tell that. So it's covered much better.
Okay, and is it more of a part of operations? That means once you have begun a project like this, you will need to actually keep updating your models for a number of months or years, so that you cover different anomalies that come in as you learn.
Yeah, so we do these model updates, and that is needed because our system is also evolving. It's suppose I trained my model for last 1 year data, right? And we put into operation, and if we do not update the models, our systems will kind of deviate, right? We might have a different feed coming in tomorrow, or some operational changes have happened, some equipment has changed. So it's not static. So that's why we need to feed in all new normal data coming in to the model, so that it could keep learning the new evolution of the process, and it remains on track. So So that's why that's how the maintenance part of the software is in place, doing it, retraining, re-updating the models.
And what is the role the cloud-based versus on-premise? I mean, what difference you face? I mean, is it which side that you use the in a real industrial case?
Yeah, so cloud-based technology is all these. Basically, that is infrastructure part. So how do you run these solutions online, right? So one option could be cloud-based. So you put all your data from plant to connect with a cloud like Azure or AWS, where your data goes and sits there, and also all these AI infrastructure goes and fits in the same cloud and get access to the data, run it and produce results, which again can be sent back to the plant and can be viewed on the URL on the cloud. So that is a cloud-based approach, and many companies adopt for it. They want to go cloud and do it, but and the problem is all these cloud clusters. For example, say they have somewhere in UK or somewhere in US, right? And some customers have very stringent requirement that I want to keep my data in my local country. I want to keep it in India. I want to keep it in Saudi Arabia. And particularly in Middle East, it's very stringent. And for that purpose, they go for a local on-premise deployment. And it is nothing different, but you are building your own local cloud, basically. So you put a server and infrastructure that needs certain virtual machines, and then all this infrastructure is being installed, and that hardware, and it does runs locally at that particular site, and within intranet it will be available, all the results and everything you can view and run. So that's the way it runs on the on-premise environment.
Okay, thanks. And how about reinforced learning? Is it really useful for the chemical engineering based problem solving?
Yeah, so so far we have not implemented it anywhere, and still we see it needs a little bit more maturity to come into application. So we are trying the methods. We are trying to see that with applications it could perform better. And the problem with the implementation in industry, you need like a very robust solutions, and sometimes reinforced learning becomes a bit finicky, is what we have seen. So so far no, but hope so we will be able to do it. Yeah.
Yeah, Dr. Ram, please go on, Ram.
Yeah, good morning, good afternoon, all. It's very fantastic speech. Thanks, Sudhanshu, as well as the AABN. Myself, Dr. Ram from Singapore. As far as concerned with the smart nation environment, AI and the other elements, without that, we cannot able to think about that. As per the process industry, Singapore is also having their own oil and gas process industry sectors. I would like to ask one simple question. How do you manage your workforce to tailor make for the country's requirement? Previously, several people also pointed out, Singapore has created their own institute, Artificial Intelligence Institute of Singapore, AI Singapore Institute. They are having the plan to create more than 10,000 of workforces, which are very much needed in different industrial sectors. It's not only oil and gas, healthcare, database with a plug and play with many elements like governance, population, as well as other elements. Data is currency, data is wealth, data is worth. So no worry about that, because earlier also my friend, he asked like, what about the security? Cyber security is also one of the important things. So holistic way, we have to think about how we can plug and play with the industrial 4.0, industrial 5.0, and so on. It will go and add on value for its own. So my worry is how India is going to build up the workforce, which are very, very important, because we don't have the thing like Singapore to import the talents from overseas and pay them as per their requirement.
and keep them as per the lifestyle what they want. India is having a lot of constraints in that. So how do you plug and play for the local workforce to be ready for those kind of things? I'm very eager to collaborate and join venture for this. Same way, we can collaborate with the Singapore government. If you are very much expertise in that kind of scenario, we can find the way how to incorporate ourselves into the Artificial Intelligence Institute of Singapore. Thank you. Over to Sudhanshu.
Yeah, so very good question, and of course, means training and workforce, and particularly in India, means as you told that we are not rich like Singapore and US, where you can attract talent from all over the world, right? So we have to do our homegrown stuff here, homegrown talent and the talent pool basically. And what I'm seeing that it's happening, and reason being. The market pull, right? That drives people learning, right? So you see there is a lot of jobs coming in, data analytics, data science, AI, ML, and everybody is aware. All the students are aware of that. And I've recently seen some curriculum of universities of India, engineering colleges of India, and they are offering courses in AI, ML. And that's good to see, and they're in demand. So I'm seeing that young people are going and they're learning it, and the advantage what I see, earlier also I mentioned, if you want to learn AI data science, it's not that difficult. Means if you have a background mathematics, some mathematics background, you have done engineering, and there is enough open source to enroll, and even there are some free courses on all this MOOC, right? So massive online open source, what we have, YouTube and all. So you could go and learn things. And personally, I'm chemical engineer, right? So by education, and also when I started working, I worked completely as a chemical engineering, all those solving those PDs and thermodynamics. But later, once I started seeing value and data science coming in, I have done my training on the job and going online, learning things, and I have not done any formal in data science. So I see that is going to happen in India also, and it's already happening, already on the way. I talk to a lot of young folks, and they are on their learning journey. So of course, if government facilitate it and do support it, we might not have shortage of workforce on this.
I would appreciate that you have also mentioned about the massive online open courses. In Singapore also, even the curricular learning pattern, they wanted to take these kind of MOOC courses, say Udemy, Coursera, EDX, and so on. It is not the problem. What myself I am addressing here is problem-based approach, because you are becoming an expert after you are handling the problems, how to find out the solution. So the AI Singapore is associated with the experts who are pioneering in AI, and they are endorsing with the industries who wanted to apply for the grants to solve something for the problem what they are having in hand. That is the way the problem-based learning is becoming more powerful to create the expertise who can able to provide the support for the needy things. That's why I wanted to ask. Curricular pattern, anybody can start any degree, diploma, whatever the certificate,
Yeah.
that is not the matter. Or you can go and study from MIT, Harvard, Cambridge, Oxford, whatever the way, it is not. But you need the project, you need the content to
Right.
work on it.
Right.
That way, because since you have been pushed into your organization for creating that, but many people seldom, they don't have that kind of opportunity. That's why we have to create the ecosystem where the local born people can be tailor made, because India cannot able to afford the fees when it is mentioning in outside India. Definitely it is not. Only the superficial earning people only can afford the course fee. But
Right.
other people, because we are expecting from the normal community who can also become the world-class manpower source for India kind of opportunity to create and surveil for them. And that is the way I am worrying, because human resource must not to be scrapped.
Yeah. I agree, and
It is
I also,
enabling for the poverty to come into
yeah.
the land. So I just worried about that because of the condition of their economy value and other things. So we can able to collaborate. AABN also can able to plug and play with that. because we are spreading all over the world. So we can able to bring those who are interested, like-minded people. We can do
That's really good, sir. And I fully agree with you that the initial learning is just a starting point, what I mentioned maybe, and then the application part where the real thing comes. So you make it work for not a Kaggle data, but for an industrial problem or real problem, and that's challenging. Means 100x challenging than solving a Kaggle competition, right? So that's what.
Singapore, why do they attract the talents to come and work? Because they are having a lot of problems where the investors who are coming to invest the money, they are looking for the talents who can able to take the journey and work on the problems to solve. That is the way the conditions is exploring a lot for attracting the world investment portfolio people to come and launch in Singapore. But India do have this kind of opportunity because we are lacking of all these kind of bridging the gap between the institute and the industry players. So we have to formulate some institute industry partnership. Together with that, with this kind of human workforce, we can able to get ready and make them to plug and play ready. Then we will be there. The projects will come like anything from other countries to India. Yeah,
Definitely.
so that's the idea I just wanted to share. Thanks for inviting me, Mr. Gopi and other people.
Thank you, sir.
Thanks.
Thank you, sir.
Vaibhav, please ask your question, Vaibhav. Vaibhav, go on.
Yeah. So can you hear me? Hello. Hello.
Yes,
Vaibhav, we can hear you. I found a lot of because their systems are not ready for of that that
Vaibhav, sir, you're breaking. Voice is not very clear. Can you put in the chat, please?
I have put up your question directly to you.
Yeah. So what would you suggest to sell solutions to particular industry? Let's say steel industry, right?
Yes.
So yeah. So the solutions what we are seeing means one category of solution is a predictive equipment maintenance. So it's uniform across industry, whether it is steel or chemical or cement. So we have all different equipments, and those equipments need periodic maintenance. So that is one solution. Definitely could fit steel industry also, and other solutions are more towards looking into whole process, finding problems upfront, as we talked about, like anomaly detection, also optimizing the overall performance of the process. So for example, you see blast furnaces in steel industry, and you want to you want to ensure that the silica content is within limit, which is the molten metal comes out, right? So AI-based solutions could be deployed there that could predict how much silica you're going to get from blast furnace, or what corrective measures you could take there. So those kind of solutions could be utilized and deployed. The example one I gave is again from steel industry, where you do DRI process optimization. So there are multiple avenues, and that needs to be analyzed and have to be seen that where value proposition is good, we get good return, and then go from there. Gopi sir, any more questions?
Hi, Sudhanshu Venkat here.
Thank you for the wonderful session. So basically, I have one question related to like this data points. Like as you explained, like to create a robust model, we need a lot of data points. And let's say for like a certain process, there are 5 critical parameters, and out of that, one parameter we can't measure. So it's quite difficult to measure. I only have 4 critical points. So in that case, how to build a robust model for that particular process?
Yeah, it depends on process and objective for what you are building the model, and many times it's AI-based models. It's possible to have a good fidelity model even if you 1 or 2 parameter missing. So we can't generalize it. Means that whether you have 4 parameter you can't build model, or you need like 10 parameter, 100 parameter. It's completely depend on the problem you are trying to solve. And of course, means you have more data, you have better, you are going to get a better fidelity model. But what you have to evaluate that with available number of parameters and historical data available to you, is your model is good enough to fulfill your requirement. So that's what the evaluation criteria should be, and that's how we should go about it.
Yep. Okay. Thank you.
I'm adding one more point to Sudhanshu. There are instances, there are instances where you can't have a real-time parameter available for model.
Yes, yeah.
Today you can predict the parameter. If you don't have and you are building it, that is the accuracy of the model. If you are predicting it, there are methods available with some machine learning algorithm. You can predict what will be the prediction output. For example, if you take in a boiler, there are certain parameter inside the boiler may not be available for direct measurement, but indirectly.
Yeah, right.
It depends upon the industry, depends upon the process. So there are methods to predict it. Again, the prediction, don't ask me whether it is 100%, at least 95% it's accurate, and it seems to be giving good results.
Okay, so which means like we can create a secondary dependent parameters on that particular process.
I can't say a secondary parameter. It is a called soft sensor. The new word is called soft sensor.
Okay. Yeah.
The soft sensor, its accuracy is 9500. If you take a cement plant, the finest prediction today, they are making it only with the soft sensor.
Okay, yeah.
Yeah, methods are available. Yeah.
Okay, thank you so much. Yeah.
Thank you, sir.
Sir, I also want ask one question in the same question. Suppose I have that 5 or 6 parameter, and I want in a single code all the prediction for 5 parameters because they are correlated. So it is possible to get the result for one only single code.
So I did not quite understand what you are saying, that your 5 parameters, all of them are correlated.
Yes, right.
So you don't want to keep correlated parameters into a model, because if the correlations are very high, right? For example, say your correlation is more than 90%, then you are giving redundant information to your model. So you should always give remove correlated variables. Only you should keep and then remove remaining correlated variables from your model input, because and many times, for example, certain ML algorithms does not work very well if you give correlated variables to it. So be mindful of that. So what you wanted to ask this about, or it was something different? Because I did not get your question very clearly.
So basically, I want to ask, like, suppose I have some heat exchanger data, right? Yeah. And there are lots of, and I want to predict the same prediction for the the actual value. So for that particular actual value, I want to predict the all the value for a particular time stamp.
Okay, so you want to take or you want to predict all parameters.
Yes.
Yeah, it's theoretically possible. You could definitely do that. It's like you could create a model which would predict one at a time, and then take other parameters and predict the remaining ones, right? So it's like leave the one you are predicting and take others and make that prediction and keep going about it. So you could make a architecture solution which can do it. So
for that, I made one code, but in that for 2 or 3 variables, the value get very shifted. And beside all the value was very good predicting, but only 2 or 3 are very shifting value. Like it's not like good prediction.
Okay. Yeah. So you can connect with me offline. I can guide you.
Okay. Okay.
Problem.
Okay. Okay. Thank you.
Thank you, Sudhanshu. I think we are taking too much of your time. Thank you for being with us on a Sunday morning. We had a lot of takeaways from the session.
My privilege to present to this group, and I'm really happy. I'm here and given this opportunity, Gopi sir.
Yeah, thank you very much, Sudhanshu. It's a pleasure. So do stay in touch with us. We'll see how to work together, you know.
Sure, sir. Keep sending me some of the
sure.
I'll join.
Sure, Sudhanshu. I should also thank Mr. Murthy, VK Murthy and NS Murthy. Both the Murthys. That's it. Thank you very much, sir. So, Mr. NSM, sir, would you like to add a few words, sir?
No, it's okay. Already too late. And thanks to you and for your wonderful work. I thought that this will be coming to 100 sooner. And second thing is that thanks to Sudhanshu for delivering the excellent lecture. Thanks, Sudhanshu, and we'll stay in touch.
Gopi, one word. Gopi.
Yes, sir. Solunga.
Gopi, Murthy our presentation கொக்கி போடுங்க.
Murthy sir பேசுறேன். I'll talk to him separately. Offline.
Okay. இல்ல ஓபன் ஃபோரத்துல ஒரு இது வச்சிருவோம்.
Okay.
So Sudhanshu, totally out of the thing context question. There's a lot of fear that AI will displace people and make people redundant and things like that. I mean, have you thought about it? I mean, nothing to do with your thing. I didn't want to disturb your flow of thoughts and answers and all that. But there's so much of fear. The surprising thing about AI is that unlike computers, which actually the people at the lower strata were bothered, people like doctors are worried that AI will totally replace them. Lawyers and doctors, they say they'll become totally redundant. What's your thought on that? I mean, this is more rhetoric.
Yeah. So, to be honest, I start with industrial domain, what we are doing, right? And what I see there. And I don't see next 10 years, AI is going to do any major job replacement of a plant operator or a process engineer or something, those kind of domains, right? So what it can do is a more like assistant. So it's like a co-pilot. So AI assist an operator to do a better job, right? So it does all those mundane tasks and also more computationally expensive tasks which humans we can't do, and give that information. And what we humans are good at, that putting all the information together and looking at the bigger picture, and that's where we add more value. So jobs, and even if you go to other domains like doctors or lawyers and all, right? So very similar analogy could be taken, and of course means there will be certain tasks what doctors do that will probably get eliminated. For example, looking at reports and finding that what is wrong, right? Analyzing the all these radiology reports, images and all. Probably AI could do a very good job as doctor is doing. But still, the importance of doctors will be there because, and they can go one level up. So where we humans are still far superior than any AI, right? So we can learn from only few data points. We don't need like gigabytes of data, right? You show a kid two picture of cat, and third picture he'll tell, yeah, this is cat and this is not a cat. It's not that easy for a AI system to do. So still humans will strategize thing, and then machine will do all kind of computational part, and together this system will be much more efficient. And that's how I see. So probably people have to reskill, but there will be some job, definitely there will be some job which will augment AI along with it in near future. I'm not talking about like 50 or 100 years what will happen, but means maybe 10, 20 years. That's the case. Yeah.
Yeah, just to add that one, because even we are working on the solution. Say, human brain, we can't see ultimately few parameters only we can see, but the AI can read the multiple places, the parameters, sensing stuff, and from that it is kind of trying to give the optimizing some choke settings. So it won't replace the workforce; it will help the solution quicker.
That's
that
right.
much I can say.
That's right.
Thanks. Very good presentation. Thanks.
Thank you.
Thanks,
Thank you.
Sudhanshu.
Thanks, Gopal.